Yeah, so if I ask you to categorize some solids on the exam, I'll definitely ask you to explain why you put them in those categories. So we have to understand not just some examples of the different types of solids, but also what's happening with the molecules and how they're attracted and how they're arranged in each type. So we've got covalent, also sometimes called covalent network. We've got molecular. We've got metallic, and we've got ionic. And so before this chapter 12, where we really started to talk about solids in detail, we had talked about ionic solids already a lot, because we talked about situations where an atom isn't stable when it's neutral. Like, for example, potassium. In group 1A, being a stable atom, it's not, or being a neutral atom, it's not stable because it needs to make a noble gas configuration that will make it more stable. So when you find potassium in nature, you don't find it as a neutral atom with one valence electron. You find it already having lost that valence electron with a positive charge because it's more stable that way. There will be things in the environment that take the electron, so it won't have it when you go to look for that atom in nature. So then if I take that and I combine it with any nonmetal or group of nonmetals that has a negative charge, then I can make an ionic solid. So just pick chlorine. So I know chlorine to be neutral needs a noble gas, or to be stable needs a noble gas configuration. So we'll make that a Cl minus, give it the same electrons as argon. So that compound is a good example of an ionic solid. Any combination of a cation and an anion makes an ionic solid. And the way that those are organized is through ionic bonds. And so the positives and negatives will line up in rows and columns. And since that's such a strong attraction, it will hold them close. That means it will have a high melting point. It will take a lot of energy to break those attractions and allow the charges to flow around past one another. It means it will be crystalline, which basically means that in the solid state the particles are organized. Yeah, they have to be organized in order for the negatives to be surrounded by positives and vice versa. I'm not just going to randomly put the charges in next to one another, because then I'd create a bunch of repulsion if positive is next to positive. So it has to be organized in crystalline. So then we talked a lot about molecules. So if you have a bunch of molecules, you're making a molecular solid. So in a molecular solid, that would be like ice, where I've got discrete molecules, or like sugar, like glucose. Right? I've got a formula that includes a specific number or discrete number of atoms that are all sharing electrons. They're all nonmetals, so these are molecules. They're all sharing electrons. Actually, glucose has 12 hydrogens. They're all sharing electrons to complete their noble gas configurations. So if they're neutral and they don't have these charges that will cause them to line up, why would they even form a solid? Well, they have partial charges, right? So they can form at least they can form London forces from temporary partial charges, but if they're also polar, they can form dipole-dipole, or if they have a hydrogen bonded to an oxygen, nitrogen, or fluorine, then they can form some hydrogen bonds. Right, so here usually, depending on the size of the molecule, like if it's a water, they will also usually be crystalline. So here they're forming intermolecular attractions to hold them together. Right, so the water molecules line up three-dimensionally, Each water molecule attracts to 4 other ones. And so in order for each molecule to make the maximum number of attractions it can with neighboring molecules, it has to be organized. So that will also be crystalline. Here, though, in general, we usually get low boiling points. I'm sorry, it's a solid, low melting points. Because here, the attractions that are holding this together in this organized structure and keeping it solidified are weaker than the attractions holding an ionic solid together. So relative to ionic solids, molecular solids usually have very low boiling points because they only involve partial charge attractions rather than full charge attractions holding it together. In a network covalent solid, here I don't have many discrete molecules all lined up next to one another. Instead, in a molecular solid, the whole thing is one molecule. And that is because each atom involved is bonded to all the other atoms through some type of network of connections, right? So it's not like each atom has all the other atoms in the solid bonded to it through millions of bonds to the same atom. That wouldn't make sense, right? It wouldn't make a noble gas configuration. It's that whatever the atoms are, so if I'm talking about glass is a good example, the silicon forms bonds to a couple oxygens, enough to make its noble gas configuration. So it might also have a lone pair here and make its noble gas configuration. Or sometimes it might form 4 bonds. And then those oxygens connect to other silicons. And then that connects to more oxygens, right? So it's a network where they're all forming a branched structure of connections in some way. I don't have discrete molecules because they're all connected. It's one molecule. Another example is like a diamond where you'd have each carbon making 4 bonds in a tetrahedral geometry, and then each one of those carbons forms 4 bonds in a tetrahedral geometry, and then that forms 4 more bonds, and that pattern extends out in 3 dimensions. Again, it's a network of covalent bonds. So the types of attractions here, talking about the types of attractions, here everything is attracted through covalent bonds. And covalent bonds are intramolecular, or within a molecule rather than between 2 different molecules. So if all the connections are intra, that means it's just one molecule. So these are usually crystalline, but they can also be amorphous depending on, often that depends on how quickly you freeze it and the specifics of the atoms that are involved. And these will have very high melting point or impossible to melt. Another example is the automobile tire. We talked about this earlier in the semester. We said each tire on your car is an individual molecule because it's made of these long chains of carbons that are kind of stretchy. That gives it its rubbery, elastic properties. And those long chains of carbons get all tangled up, and then they get connected to one another with sulfur atoms. So they're all, these long chains, all the carbons are connected in a chain, and then one chain's connected to another chain through these covalent bond linkages. So how do you melt that? How do you get the chains to be able to flow past one another when they're actually connected through covalent bonds? You can't. You have to break the covalent bonds. That requires that you burn it. So if you want to, what do you do with old tires? You can't really recycle them. So sometimes, yeah, but you can't do it by melting them down and reforming them like you can with a lot of other plastics. So if you heat up some plastics, you heat them up, they convert into a liquid, and then you could just remold them into whatever new shape you want them to be in. But with a tire, you can't do that because you can't melt it. It has to be burned in one way or another to break the sulfur covalent bonds and allow the chains to then flow around and become a liquid. So then the last type is a metallic solid, and so this is just metal atoms with no nonmetals involved. So just take any metal on the periodic table. Maybe I'll take silver. So this is just a bunch of silver atoms that get close together and form a solid. Since each atom in this solid is the same and they're all spherical and it's not difficult to organize them, like you could think about when you're a kid and you had like a toy, you might have played with a set of blocks, like building things with blocks. When you're done building your stuff and you throw all the blocks back in the toy box, they don't just like line up, right? Even though all the blocks are the same shape, if you throw them in randomly, they don't line up too well. So what do you have to do to fit them all back in the box that they normally go in? You got to shape the box, right, so that they slip down into the holes and line up. If those blocks were like magnets, where the opposite ends attracted and they were able to attract one another and those attractions caused them to line up, yeah, well then they would line up in an organized way. If you were thinking about like little like ping pong balls instead of blocks, and you throw a bunch of ping pong balls into a box and you shake it a little bit, those should line up pretty well because the ping pong balls are attracted down by gravity, and so if there are little gaps, they fall into those gaps and form a relatively organized structure. So there's no reason why this shouldn't be crystalline, because the particles that are organized are forming attractions, and because they're all spherical, it's very easy for them to fall into place and get close to one another through those attractions. So the types of attractions, the book describes them as metallic bonds, and that's kind of a new term, but the way that we described that when we talked about it, you don't really have to know that term. It's important to be able to understand what's happening, though, and that is that if we think about each atom of the solid, so if we're looking at silver, for example, like there's like 47 positive charges in its nucleus. It's got its outer electrons all the way out to the 5th energy level. Right, so I'm using this yellow to be like the cloud of electrons. It's going to be pretty far out from the nucleus. And the 5th energy level electrons, there's only one. It's going to be very loosely held. It's going to experiencing that one electron in the 5th energy level is going to experience a lot of shielding from all the other inside energy levels, and that's a similar thing with the other metals. Their outer electrons experience a lot of shielding. So the outer electron is really pretty free to move around. It's not held that tightly to that nucleus. So when I add another atom and think about its electron cloud, that outer electron on this one, it's not really held much more tightly by this atom. It's in that orbital. Its electron density is held mostly pretty far out from the nucleus, experiencing a lot of shielding. It could instead just go over to the other atom. And that would create now a vacancy for this atom. And so maybe from the other side, a neighboring atom, maybe one of those electrons, moves over here. So we get this ability for the electrons to flow even more than they normally would. So metallic bonds are a little different from the normal types of attractions. Normally when we think about attractions, we think about charged particles lining up to attract, maybe partial charges attracting, something like that. But here, the atoms stay together because their electrons are flowing over all of them. Right? When we think about an orbital, electrons are in an orbital, we think about the electron density being spread around that nucleus, right? In the orbital, the electron density is that negative charge associated with that density is attracted to the nucleus of that orbital. But here, these atoms have to stay lined up because the electron density, it's not just experiencing a negative positive attraction to that atom, it's experiencing a negative positive attraction with a lot of other atoms around it at the same time. So it's hard to break those atoms apart because the electrons are not always in any one position and they're feeling and experiencing attractions to a lot of different positives at once. So it's easy for those attractions to stay formed if the atoms stay together and line up and that stays in the solid state. So those often will have a high melting point as well because it takes a lot of energy to separate these atoms when their electrons are kind of holding them together by being spread out over the entire surface of them.